Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video, we're going to talk about bending resistance. We're going to start talking about it anyways. We're going to continue this across probably a few videos in order to get the whole thing together in reasonable sized chunks. So first I'm going to talk about the phenomenon, or the phenomena, plural, that are involved in our bending resistance equations. Then I'm going to talk explicitly about what the bending resistance equations are in O86 and how they compare for lumber and glulam. And then I'm going to start talking about the size effect for bending in glulam specifically, because in lumber it's pretty straightforward. So let's get started. So as I said, there are two different phenomena that we are looking to find the strengths for when we're calculating bending resistance in timber. Okay, so the first of these two is the section moment capacity. And by section moment capacity, I mean basically local moment failure caused by stresses in the fibers, the stresses that are caused by bending. And we recall that if we bend this beam by, let me say I rotate the ends, one in one direction and one in the other, then I'm going to get tension in the bottom if I'm rotating it this way. I'm going to get tension in the bottom and I'm going to get compression in the top. We're all familiar with that concept from mechanics. And so I can fail in tension in the bottom by pulling the fibers apart, and I can fail in compression in the top by crushing the fibers at that extreme fiber surface. So if I remember my mechanics, here I'm looking at the cross-section, not the cross-section, I'm just looking at the end of a beam at a cut, like if I'm taking a free body diagram of that beam and I cut it somewhere where there is internal moment, and if this is the resultant moment at that cut section, then I can recall from mechanics that I can draw the strain distribution, and it should look something like this, where this green line is the neutral axis. Let's call that neutral axis of the member, which for a rectangular section is just right bang in the center. So here I have the strain, and our strain profile is linear. And remember, typically for typical members in construction, we are assuming that these members are Euler-Bernoulli beams, so that plane sections remain plane, and our strain profile throughout the depth is totally linear, and we have compression on the top in this case and tension in the bottom, and in between our strain has a linear profile, and at the center where we have the neutral axis we have zero strain. So then if I want to look at the stress in the beam, as long as I'm still within the linear range of the material, so I haven't started to crush anything or haven't gotten high enough that I'm starting to have a loss in stiffness, then my stress is going to also look like that. So this is explicitly the stress that's in the linear range of response. And this one we can call sigma. And you'll recall that if I want to calculate the strength of this, I need to look at the distance to the extreme fiber on either the tension side or the compression side, depending on which failure I'm looking at. And remember that if we want to relate the strain to the stress, we have this equation, which is a constitutive relationship between stress and strain, where the stress is Young's modulus times the strain. And this is all easy basic mechanics. And another equation that you will hopefully recall for calculating the stress is my over I. I won't go over the derivation of this right now. You can go back to your mechanics course. So if I wanted to calculate the moment resistance, like let's say that stress is a limiting stress and I and Y are geometric parameters, then I can calculate my moment as stress times I over y. Where, of course, I is the moment of inertia. Well, we typically call the moment of inertia, but it's really the second moment of area. And y is the distance to the extreme fiber, as we said. And we recall that there's also a simplifying parameter that we can use here, which is s, which we call the section modulus, which is simply I divided by y, where y is the distance to the extreme fiber. And in this case, for a rectangular section, and almost all timber members are rectangular, which is the nice thing about them, then y is h over 2, half the total height, since the neutral axis is in the center. So then if we sub back in, we're going to get mr, if we want to find a resistance, is basically proportional. I'll say proportional here because we're missing some parameters, but it's basically proportional to s, the section modulus, times sigma u, which would be the ultimate strength of the wood in tension as a stress. So we're going to see that basically come back when we look at the actual equation for moment resistance for timber. We're going to see S, and we're going to see something that is effectively sigma U, which of course for us is our strength F, small f, which we modify by a bunch of modification factors. So that's the basis of section moment capacity for timber, and in fact for any kind of beam. Next, we need to consider lateral torsional buckling. So if you're familiar at all with beam design in another material, like in steel or concrete, then you are familiar with this phenomenon of lateral torsional buckling. And if I bring up my ruler here, okay, lateral torsional buckling is what happens when I have a section that is quite slender, and when I push down on it, it wants to buckle to the side. You see, like when I push down on this, I'm resting it on my shoulder and on my hand over here. When I push down in the center, it's very hard to get this section to fail. What happens instead is I push on it and it wants to just twist and go off to the side. And that is very common in deep sections. Now, of course, that is not possible if I bend it like this. When I just push in the center, it's always going to go straight down. And this way I can easily get a moment failure from section moment capacity in the center. But if I turn it the other way, then it's very likely to want to bend outward if I don't restrain it. In order to get this to fail in section, I would have to restrain this all the way along to prevent it from buckling out of plane. And that is the phenomenon of lateral torsional buckling. So obviously this is very related to the geometry of the member that we are looking at. So we can expect that geometry is going to come into play when we calculate our lateral torsional buckling strength. And it's a buckling phenomenon similar to when we talked about compression buckling, but a little bit more complex, because compression buckling, we have this single simple buckling mode, and in lateral torsional buckling, we have a lateral movement, but we also have a twist. And that's why it's called lateral and torsional, because of the twist. So if I were to draw this beam going off to the side, and this is a bit difficult to draw, it's going to look like this. But first of all, I've drawn this green beam straight up. When I add a load to it, I'm going to add a load in the center here. And those little X's are just indicating that it is laterally restrained at the end. So here it's like I have restrained the top. So it's sitting on a pin, so it's restrained at the bottom. And then I will also restrain the top so that the top can't move laterally like this. It can't do that. And when we design timber beams, we always have to restrain it like that, no matter what. So all timber beams, you'll see when we talk about moment resistance for lateral torsional buckling, all of the cases assume that it's restrained like this, so that it's restrained at the top and bottom, at least at the ends, where it's bearing. So there's my best artist's rendition of a beam twisting and lateral torsional buckling. And so you can see that the bottom of the beam over here, it twists sideways a bit, but really predominantly it's the top of the beam that's going over. And the reason that it buckles is because, as we said, when we bend on a beam, the bottom is in tension and the top is in compression. So basically what's happening is the top, since the top half of this beam is in compression, it can buckle just like a total column in compression can buckle. So we have a buckling phenomenon happening, but just on the top. So the bottom can stay, tends to want to stay straight because it is in tension during this process. And it's the top mostly that's going to move over. But the bottom, of course, is going to move over too because it has to follow the top when it twists. So as I said, it's quite a complex phenomenon in that sense. We have a twisting and a lateral movement happening together. And if I look at the section on the right here, then you can see where it starts green, starts center. When I push down on it and it buckles to the side, we get both a lateral movement, and on top of that, we also get a twist. So that's why we call it lateral torsional, because it has both lateral movement and torsion. And we're going to learn how to calculate those effects. Okay, so between lumber and glulam, there are a number of similarities in the way that we approach bending resistance, and the equations are close to identical, but not quite. And it's because of different mechanical effects happening in lumber and glulam, particularly to do with the size effect in both materials, because the size effect for lumber and the size effect for glulam, in this case, come from totally different mechanisms. So if we just look at the lumber side, you see we have phi, which we always have. That's our resistance factor. And then we have FB and S. And FB is basically our stress, our strength in terms of stress. So in the previous equation we looked at, that is our sigma U, our ultimate stress capacity. And S is S. It's our section modulus. So you can see right away we have exactly what we expect to find in a bending resistance equation. Then KZB is our size effect. And that size effect we get directly from our table 6.4.5, which we are very familiar to using by now. Looks like this. So you can see that we have size effect for bending and shear here. And basically, depending on the size of our beam, smaller dimension and larger dimension, we can pick out what our size effect factor is. So no difference there from other size effects for lumber that we've gotten out of this table. And then the KL, which we're going to talk about at some length and are going to require a separate video to talk about in detail, is our lateral stability factor, which is the factor that accounts for lateral torsional buckling. So when we're talking about stability, sometimes what we're talking about is buckling, because buckling amounts to a loss of stability. So that's why it's called lateral stability factor. And based on the geometry of our beam and also the strength, depending on which buckling regime we're in, we are going to calculate a KL, which is going to reduce our MR to account for buckling. Just like when we calculated for compression buckling, we had our slenderness factor, which also reduced our strength to account for buckling. So moving on to glulam here, we're going to talk about the differences in size effect in a minute, but in glulam we have two different equations, MR1 and MR2. We have to calculate both and then take whichever one is the minimum. And you'll notice that it's very similar to lumber. We start with phi, FB, and S, which we expect. And then we have both equations also have a factor called Kx, and this is to account for curved glulam members. So when we curve a piece of glulam, we have to curve the individual plies of the glulam, which means that we have to bend them, which means that when we bend them, we put some stresses in the beam. And those stresses that exist from the process of curving the glulam take up some of the strength that can be used to bend the glulam when it's actually in place. So if I want to bend it further, obviously I've already bended it some, so I can bend it a little bit less than if it had started out straight. We're not going to cover that in detail at this point in the course. We might cover it as a bonus topic, but potentially near the end. So for now, our kx is always going to equal 1, because we're going to assume that there's no curvature to our beam and we're just talking about straight beams. But here's where the big change is. One of these equations has kzbg but no kl, and the other equation has kl but no kzbg. Why is that? It's because one of these effects in glulam, the size effect, is not the same as the size effect for lumber. So in lumber, our size effect is based on grading, as we discussed, and how bigger members are more difficult to grade accurately because we can't see inside them. For glulam, this size effect is a bit different because we know glulam is made of smaller pieces all glued together. So basically for size effect here, the effect that's happening, like there's still a size effect that exists and has been shown in experiments to exist, but the reason it's happening is not because of that grading issue. Instead, it has to do with the failure of the joints on the tension side of the member near the ends of tension zones. So as I bend this down, I have tension in the bottom. This glulam member is made of all sorts of individual pieces all glued together, and the joints at the end that hold those together have a tendency to fail more when the beam is bigger, for whatever reason. But the reason has been the effect has been shown to occur experimentally. So that means that size effect in glulam is a tension side only phenomenon. It occurs because of a mechanism that is failing beams early when they're deeper on the tension side near the end of a tension zone. The KL factor, in contrast, is a compression side only effect because it has to do with compression buckling of the top of the beam. When I have lateral torsional buckling, it's the top of the beam that acts laterally. So if I'm looking at the strength for lateral torsional buckling, which happens on the compression side, the tension size effect is not going to affect that strength because it's only happening on the compression side. Just like when I look at what's happening for size effect, which is a tension side phenomenon, the lateral torsional buckling is not going to affect that strength. So they're happening on two different sides of the beam. So that's why we don't multiply one by the other. We look at them separately in two separate equations. This is in contrast to lumber, because in lumber, the size effect is for the entire beam. It's for the entire thickness of the beam, tension side, compression side. The size effect is for the overall strength due to this grading issue. So that's why on the lumber side, we multiply the two together. So there is an equation for size effect in glulam, and it is an empirically derived equation. Okay, so that's some long notes to explain what I was talking about. Now I've given the equation for kzbg, which is clearly an empirically derived equation because of the 1/10 exponents. We don't have many physical phenomena that give an exponent of 1/10. So this is some kind of curve fit, and the sizes that are there, 130, 610, and 910, are based on the baseline size of a piece of wood that they tested in order to determine the size effect factor. And we are going to talk about size effect for glulam in a bit of detail in a minute, because there are some peculiarities to determining the factor L, which is the length of the tension zone, not the total length of the member. We're going to go into that in detail. And this is capped at 1.3. This is a numerical cap, so that means if I get a kzbg that's greater than 1.3, I just set kzbg equal to 1.3 and continue the calculation. So again, for lumber, we have a single equation that includes both size effect and lateral stability because they interact in terms of strength, because size effect affects the entire beam depth. And for Glulam, we have separate equations, one that takes into account size effect, the other which takes into account lateral stability, because those two effects are on the tension side and compression side of the beam respectively, but separate, and they don't interact. Okay, so that's size effect. So that's KZB on the left and KZBG, G for Glulam on the right. And the last thing we're going to compare here is lateral stability factor for both. So we have lateral stability KL on the left, lateral stability KL on the right. So for lateral stability for lumber on the left, this KL right here, we have two options basically for calculation. And for lumber, it's probably most common that you're going to use the first option, which is simplified criteria, where basically we are given a set of requirements that we can use to restrain a beam or a joist properly so that we don't get lateral torsional buckling instability. So if I have my beam and if it's totally unrestrained and I push down on it, then it's going to buckle laterally. But if I can restrain this from moving out of plane at multiple points along the length, for example, then it can't do this, and therefore I'm going to be able to get the full sectional strength. So that would mean that KL equals 1. I don't have any lateral instability. And depending on the geometry of this, depending on the depth version versus the width of this beam, I have different requirements for how I must restrain that beam in order to get that KL equals 1. So if I can fit in any of those categories, then KL equals 1. If I cannot fit in those categories, that doesn't mean that the beam is not permitted. It just means that I have to actually calculate my KL manually. And in the Glulam section, there is a calculation method for how to calculate KL, depending on the beam geometry. So just like for beam compression, we had a slenderness. For beam lateral torsional buckling, we also have a slenderness factor that we can calculate, and that can give us a KL that's not equal to 1. So I can do either case. So for Glulam, I also have two options. One is if my depth to width ratio, so this is basically my aspect ratio, my depth divided by width is less than 2.5, which means kind of a more square section, still rectangular, but closer to square. Then I can just assume that my KL equals 1, as long as I have given proper restraint at the ends, which applies also to lumber, by the way, and we're going to talk about that in detail. If it does not satisfy that criteria, then basically I just use that same calculation, which takes into account bending slenderness, to calculate a KL that's not equal to 1, so that we can reduce our strength appropriately. The last parameter on the Glulam side is this KX, which I mentioned briefly. I'm just going to put in the note here in the interest of completeness. So again, the curvature factor KX is to account for curved beams. If we don't have a curved beam, then KX is just set to be equal to 1. Now, that's not if I do have a curved beam, that's not the only thing that I have to do is consider KX. There's another strength criteria that I also have to satisfy, which is a radial strength criteria, which we're not going to cover, but you'll find that in the... So if you want to learn for yourself about how to do curved Glulam members, we first have to use KX, and there's a calculation for KX, which depends on the plies. And that takes into account the residual stress caused by the bending. And then there's also a radial strength criteria, which accounts for the section wanting to separate perpendicular to grain when I bend a curved section, specifically when I want to unbend it. So you can look into that yourself if you like. Okay, and then there are some parameters that are common to both equations, which are the usual suspects. We have phi, which is our strength reduction factor. accounting for material properties, and we have a capital FB, which is just the same as every capital F we've seen before, which is just a small FB, which is our material strength that we get from the tables, 6.3.1, A through D, or 7.3 for Glulam, and all our usual strength modification factors, KD, KH, KS, KT, which I'm sure you're getting used to saying now after doing this so many times. Okay, so just to finish up this particular video, we're going to talk about the size effect for Glulam, and then we're going to follow up with detailed calculations of the lateral stability effect after. Okay, so we're just going to talk about specifically bending size effect for Glulam, because as we remember, size effect for lumber, we just pull out of this table, which is very easy. But size effect for Glulam is a bit more complicated because A, we have a calculation, and B, the definition of L is explained, but not necessarily obvious. So I'm going to give some examples of what that would look like for different cases. So as I mentioned before, this is an empirically derived equation. And since it is, like other size effects that we've seen, like the size effect in compression, also were empirical equations, which are curve fits based on test data. The units that we put in here are going to matter because we have these exponents of 1 to the 10th. So basically all of these units have to be in millimeters. If you use meters for length by mistake, then you're going to get quite a wrong answer for size effect. It's not going to be the right answer. So B is the width. It's typically the width of the section. If I have, sometimes I can have, so for if I have a Glulam section that is quite big, quite wide, then I mean usually like you are familiar with seeing Glulam sections that look like this, where the B is the entire width of the member. Like my individual plies, they go from side to side. But there are some bigger Glulam members, or actually some of the Glulam members that are in the East are made up of a number of small elements all the time, where instead of it looking like this, it actually looks like this. So we have smaller members, but we might have 2 of them side by side across the width. So if that's your case, then your B would be this right here. That would be your B, and this whole depth is your D. Okay, and then beam segment length is the bit here where I'm going to spend a little bit of time to show you exactly what that means. So as I mentioned though, KZBG is defined relative to some tests where they tested a bunch of sizes of beams to find out size effect, but their baseline beam was a 130 B, like a beam that was 130 wide by 610 deep by 9100 long. So 9 meters by 610 deep by 130 across. And that's why the equation looks like this. Okay, so that being the case, now I'm just going to give a few examples for determining L for the use in the size effect equation. I'm going to look at 2 simple cases here. One is a simply supported beam. The other one is a multi-span indeterminate beam. And let's look at what is the moment diagram for these 2 beams, because you know up here it says beam segment length, where the segment is between points where moment in the beam is 0. That's internal moment in the beam is 0. So in order to find that out, we need to know the moment diagrams. Okay, so the one on the left, this is assuming you know how to draw this moment diagram. I mean, we have no numbers here, but I think we can figure out just qualitatively what these moment diagrams should look like. for now. The segment length is the entire length of the beam because the moment is 0 here and it's 0 over here. And the segment between is the length L that we're going to use for calculating size effect factor. On the right, the moment diagram looks like this. So we have a few places where the moment equals 0. And so this is going to be one segment length. And this one in the middle here will be a separate segment length. And then, of course, we'll have this one on the end too. So depending on geometry, you know, these might all be different. Okay, one other interesting thing that happens here is, you know, on the left segment, segment 1, I have tension in the bottom of the beam, right? And then in segment 2, I have tension on the top of the beam, and on section 3, I have tension on the bottom of the beam again. But there's always some tension side of the beam, and so we're always going to consider some KZBG. And each segment has a different KZBG. So what's the consequence of that? Basically, for each segment, I'm going to have to calculate a different moment resistance. And that moment resistance will be compared to the maximum moment within that segment. So I'm going to have an MR for segment 1 and an MF for segment 1. And I'm going to have an MR for segment 2 and a different MF, right? Like this is the MF for section 1, segment 1. This is the MF for segment 2. So each section has a different KZBG. Somehow KZBG is the hardest thing in this whole course to write down legibly. And therefore a different MR. Okay, so that's the end of this segment of the video. We talked about moment resistance for lumber and for glulam, and covered in detail the size effect factors. In the next video, we're going to cover the lateral stability factor, KL, for lumber and for glulam.